Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In this episode, we are going to add render items to the engine. Render items form a link between geometry submeshes, materials and other data, such as transform matrices. We start by adding some constructs that make gathering this data easier in the first place, and then we'll implement the code for render items. In this video, we are going to introduce functions that will read the data in our data structures, which is needed for rendering objects. Looking at what we have so far, we see that we pack our geometry data in blocks of memory in this format, with references to the submesh data for this geometry. The submesh data contains mainly information about the content that's uploaded to the GPU. We also have materials which have a similar format, in the sense that they are packed in blocks of memory with references to shaders and textures. If you haven't seen the videos where I explain these data structures in more detail, feel free to stop the video and watch those first, because you need to be familiar with how and why the data is packed this way in order to understand the code that we are going to write in this video. Looking at how the data is allocated in memory, we see that most of the time our memory blocks are allocated separately and therefore could be scattered in the memory. Sometimes we do manage to pack them in an array, which is better. As we know, keeping memory allocations close to each other improves cache coherency. However, even if you would succeed in packing all our information in a contiguous block of memory, rendering a scene inherently makes it impossible to access data sequentially. For example, in this scene from an undisclosed video game, you can see that the data that we need to access for rendering highly depends on where in the scene the camera is looking. Here we can see clearly that even for the data in an array, the access is quite random. And it's even worse when we have to go through this data multiple times for different render passes. We can improve this situation by going through the pain of reading this data once, and then cache it in a way that can be used sequentially. Although data access is random for different camera views, it is completely determined during the same frame. So if we would cache everything in camera's view for the current frame, we could read it sequentially as often as needed, which in theory would cause fewer cache misses. In the first half of this video, we'll construct these caches for submeshes and materials, and then we continue with implementing render items. We start with a function that will take a geometry hierarchy index and return an array of GPU IDs for submeshes that belong to that geometry. We'll create one render item for each of those submeshes. We also need a function that will give us the LOD offset information so that we can pick the right submeshes to render depending on the LOD threshold. I'll have to move this LOD offset structure to the header file in order to use it as the output for this function. Note that it takes an array of geometry hierarchy IDs and an array of thresholds. This is because we are going to call this function each frame and we don't want to make one call for each object that we are rendering. This will save us CPU cycles. We have to implement these functions next. We lock the geometry data so that it's not modified by another thread while we are reading this data. Then we take the pointer to the geometry hierarchy and test if it's a real pointer or just an ID. Most of the time we'll find that it contains an ID, since most objects in a game have a single submesh and no additional levels of detail, but obviously that can vary per game type. If the pointer is really a pointer to a geometry hierarchy, we can read it using a hierarchy stream object and copy the array of GPU IDs. I'm going to assert that the ID count that was given to us as the function parameter agrees with what we found in the geometry hierarchy. Because we need several lines of code to do this, I'll put it in a lambda expression that returns a boolean. Now we can move on to the next function. Here we check that we have valid parameters and that we are referring to an array of LOD offsets that's empty. After locking the geometry data, we look through the array of geometry IDs and extract the LOD offset information. Same as before, we check if the pointer to the geometry hierarchy is fake or real. If it's fake, it means that we don't have any extra LODs. Therefore, the offset is 0 and the count is 1, which indicates that we have a single submesh. If it's a real pointer, we use the hierarchy stream to read its data. We can use the LOD threshold value to determine which LOD offset we need to return. I also have a small fix for the LOD from threshold function, which should return 0 if there is only a single LOD in the geometry. This is all we need to do to get the submesh GPU IDs and the LOD offsets for an array of geometries. Next, I'm going to add a cache structure to each type of content that we have, with the purpose of making it easier for us to sequentially access the data that we need for rendering. Basically, this is going to help us turn the scattered buffers and arrays of structures into structures of arrays, which are much faster to access. Starting with submeshes, we'll have arrays of position buffer pointers, element buffer pointers, index buffer views, primitive topologies, and elements types. Then we need a function that takes an array of submesh GPU IDs and gathers all this data in views cache. As you can see, we have this information in the vertex buffer views, and as it turns out, we'll only need the buffer's GPU address in order to render our objects. The same is true for the element buffer. However, we do need the full index buffer view for rendering. For the getViews function, we check that the function parameters are valid, lock the submesh data, and loop through each submesh view and copy the data that we need. Although we have to touch the submesh views non-sequentially, we only do it once, whereas we'll need to access the cached data multiple times, which is in theory much faster. Now we have to do the same for materials. In this case, we only need to know what root signature and material type belong to each material. And we need a function that will gather this information for an array of material IDs. This is similar to what we did for geometry hierarchy data, except now we don't have fake pointers and it's simpler to extract the data. We use a material stream object to read the material data and assign them to the fields in material caches. Fixing a typo here, and we also need to have the correct type for this array, which needs to be a pointer to root signature pointers. Well, that's it for the content caches. We probably have to do something similar for textures in the future when we are able to import textures. However, now we can move on to constructing render items. We use low-level render items to tell the renderer how it should render the submeshes that make up the scene. Obviously, we need to give the renderer the submesh data, but it also needs to know which shaders to use and which textures to sample from. It also needs a transform matrix in order to position the submesh in the scene. We can provide the renderer with a set of IDs that can be used to gather this information. This set of IDs is the low-level render item, which is created per submesh. That means that a geometry that consists of one or more submeshes will result in a list of render items. We can put the indices to this list of render items together with the ID of the geometry in the block of memory and add a pointer to that into another list. The index of that pointer in this list is the render item ID for the whole geometry. A low-level render item is simply a collection of IDs. It has the entity ID so that we can look up the transform information for the rendered object, the submesh GPU ID, which is used to get the vertex and index buffers, material ID of the material used to render this submesh, and two pipeline state object IDs, one for the depth prepass and one for the gpass. Here we are going to also introduce a cache structure right away. This is almost exactly the same as the render item, except it's a structure of arrays, and instead of PSO IDs, we have the pointers to the pipeline state objects. Next, we need the low-level functions that add and remove render items. We'll also need a function that will give us a list of render item IDs for submeshes that need to be rendered. This information is contained in the frame info structure, which I yet have to define. Okay, let's add the frame info structure, though I thought I already defined it somewhere. Let me do a quick search. Oh, it was the 3D12 frame info. That's the low-level counterpart of frame info. Well then, frame info has a list of high-level render item IDs, not to be confused with the low-level ones that we just added. The frame info also has an array of thresholds for each render item, from which we can determine which LOD needs to be rendered. We also need the render item count and the ID of the camera that's used to render this frame. Now let's implement these functions. Starting with the function for adding render items, we need to look at the geometry and create one D3D12 render item for each of its submeshes. I'm going to quickly document the output format of this function first. It will allocate a block of memory that's just an array of IDs. The first ID is the geometry hierarchies ID, followed by an array of one or more D3D12 render item IDs. The array is terminated by an invalid ID. Remember that we need to pair one material with each submesh in the hierarchy, and therefore the number of material IDs must be the same as the number of submesh GPU IDs. We can use it to allocate enough space on the stack where we temporarily write the GPU IDs. We can use getSubmeshGPUIDs function, which will write the GPU IDs for the geometry into the array that we allocated here. Next, we allocate stack memory for each array in the submesh views cache. Note that although we are allocating stack memory, which we must be careful about, we are merely getting information about one geometry which never has a huge amount of submeshes, and it should be okay if we do it like this. On the other hand, this is not a part of render loop or any hotcode path that needs to be super performant. So if you prefer, it's also okay to use vector arrays instead of stack allocations for this. Next, we call getViews function that will take our array of submesh GPU IDs and write the relevant information about each submesh to our cache. Now we are ready to allocate the memory block for the array of render item IDs for this geometry. As I mentioned, the array should be large enough to contain the geometry ID plus one or more render item IDs terminated by an invalid ID. We can already write the geometry ID into the buffer, and we take a pointer to the next elements, which will contain the render item IDs. Before we can continue, we need to add the data containers for render items. First, we need a free list of the 3D12 render items. In addition, we need a free list of render item buffer pointers that link each geometry to the corresponding D3D12 render items using their IDs. We also need an array of pipeline state objects. Similar to materials and their root signatures, this is not a one-to-one mapping, and we need an unordered map to quickly look up pipeline states. I'll explain this in more details in the next video when we create the pipeline states. Finally, we need a mutex for synchronization. After using the mutex to lock the data, we can go ahead and create a D3D12 render item for each submesh in the geometry. Note that unlike the geometry ID, we are repeating the entity ID for each submesh. Although this uses a bit more memory, it makes it easier and quicker to process the data for rendering, as we'll see in the next episode. So we copy the entity ID, submesh GPU ID, and the material ID that's used for the submesh. The remaining part of a D3D12 render item is creating the PSOs, which we'll do later. Assuming that we'll manage to do that successfully, we can add the render item to the items list and write its index into the buffer. We mark the end of the list with an invalid ID and add the buffer pointer to the list of buffers. To remove a render item, we go through each render item ID and remove it, and finally remove the buffer itself. Again, we don't remove or release the pipeline states, as they can be in use by other render items. We release those when the renderer is shut down. Actually, let's write that code now. Here's a part that I forgot to do in the last episode, and that's when we release the root signatures, we also need to clear the material root signature map and also remove the root signature pointers. And we do the exact same thing for pipeline state objects. The next function that we need to write is one that takes the array of high-level render item IDs in frame info and returns a list of D3D12 render item IDs. This function will be called at least once each frame, and therefore it needs to work fast. So in order to eliminate memory allocation, I'm going to add a little frame cache here specifically for this function. It contains arrays of LOD offsets, geometry IDs, and thresholds. We'll see how this is used in a minute. Before we start, we empty the cache. Then for each render item, we write the geometry ID and the thresholds to the cache. And we can use these arrays to get the list of LOD offsets for all geometries that we are going to render. From LOD offsets, we can calculate the total number of render items for this frame and use it to resize the vector that holds the render item IDs. In our implementation of the vector container, resize will only allocate memory if the internal buffer is smaller than the needed size. So we can rest assured that there won't be a lot of memory allocations, because this is basically a grow-only buffer. As a final step, we go through all render items for each geometry and only copy the render item IDs that belong to the selected LOD. The last function that I'd like to write for today is a function that takes this list of render item IDs and gathers the render item information in the items cache. This is a fairly simple function that locks the data and looks up the D3-D12 render items for each render item ID. Then it writes the data from each render item into the cache. Okay, let's stop here for today. The only part that's left to do is the creation of pipeline state objects, which we'll be working on in the next video. As always, thank you for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!